All right. Okay, so last time we were discussing diagrammatic perturbation theory, which is the basic technique that is used in all many-body physics, ranging from statistical physics, like we're doing here with particles bouncing around in a box, to electrons interacting in a solid, to elementary particle physics. All of these things use variants on these same techniques that I was showing you. And there's two miracles that happen in all perturbation theory calculations. One of those miracles is the one I showed you last time, which is known as the linked cluster theorem. And that's the result shown on the left-hand panel, namely that if you have to sum a whole bunch of graphs, diagrams, there could be Mayer integrals, there could be Feynman diagrams, whatever it is that is the setting, there could be Wild diagrams in that's WYLD, in fluid mechanics and turbulence, all of those things. The basic rule is that if I want to sum all the graphs, all I have to do is compute the connected graphs, because e to the connected graphs equals all the graphs. And you can prove that just from graph theory, and that's separate from knowing how to evaluate the integrals. It's just a consequence of the way graph theory works. So that's the first miracle. So today we're going to talk about the second miracle of many-body theory. I'm going to scoot through it. You will not be able to follow the algebra. I want you to just follow what it is that we're trying to get. And that's the most important point. And then I will show you that we get a thing called the cluster expansion, which is a way to really compute the virial expansion in detail and compute systematically to any order that you want the corrections to ideal gas behavior. So we're going to look at that, and then I'm going to show you why it doesn't work, how it fails. As I was saying to Professor McGreevy just before class, some of you were still here, he was just teaching Feynman diagrams in his quantum field theory class, and I said, well, the only thing that Feynman diagrams are good for is when they break down. And he said, oh, I don't know if that's true. And then I said, well, all the interesting states of matter were discovered theoretically by non-perturbative methods. And he said, yeah, that's fair. And then he said, yeah, in fact, what I was just showing was how these diagrams get bigger and bigger as you know, in the behavior that he was discussing in superconductivity, and therefore then they break down, and so you can't describe the state using Feynman diagrams. So that's exactly this situation I'm going to show you today. That again, the diagrams, when the things are interesting, the most interesting questions that you can ask cannot be answered by these techniques, but their breakdown can tell you something about the answer. And so that's my main point. We'll talk about there's two places where they fail. One is to do with phase transitions, which we will not do today, and the other is in systems with long-range interactions, charged fluids, for example. So we'll talk about that. And I'm going to briefly, I don't know if I'll get to it today, is talk about what is known as Debye-Huckel theory, which is the physical chemistry of charged electrolytes. And what we're going to encounter there is the first time that you'll ever see a real renormalization calculation, a charge renormalization, but you'll see it come out of high school algebra, very simple physics. All right, so let's leave on where we left off. So what we did was we calculated the grand partition function. And remember, the reason we got the grand partition function was because when we tried to compute with the Boltzmann distribution, we ended up with a horrible formula involving diagrams and so on, but it was a constrained sum. And we remembered what we were taught last week, that if you have a constrained sum, the answer is just do the grand canonical distribution, and that gets rid of the constraint and makes everything factorized. And that's exactly what happened here. So even though we were looking at a diagrammatic expansion, the same thing happened, and we were able to get this. So why do we care about the grand partition function? Well, we care about the grand partition function because when we take its log, then we get the pressure, and that's the thing we're trying to compute, the equation of state. So now let's continue on with our calculation. So now that we have chi, we can calculate the equation of state, i.e. the pressure dependent on density. And And as usual, there's going to be a problem because our formula for chi involves the fugacity, as you can see on the left-hand side. So we also need the constraint equation. To get the fugacity. So in a nutshell, so the summary of the next part of the lecture, in a nutshell, what we're going to do is this. We're going to write down the constraint equation. And then we're going to eliminate lambda between the equation of state for P and the constraint equation. And that's going to involve dividing two infinite series. And then then a miracle happens. And that's what I'm going to do. So I'm going to very quickly just go through that and then get to the point where we can talk about the miracle. So let's just quickly do that. And if you want to go to sleep, feel free, and I will wake you up when I get to the good bit. Okay. So here we are. I'm going to write down the equation of state. So what we know then is that 1 over v log of chi. So that then is then by definition 1 over the thermal de Broglie wavelength cubed, and then the sum over clusters of BL lambda to the L. So that's the equation that I derived last time, taking the log of it. And then if I differentiate with respect to lambda, so the constraint equation, which to get that I differentiate with respect to the fugacity lambda, and so I get that lambda over v d log of chi by d lambda. So that is then just 1 over lambda t cubed times the sum over L of L BL lambda to the L. Okay, so that's that. And so then I can now write down the physical equations. So therefore we know from physics that P over KT is then 1 over the thermal de Broglie wavelength cubed, and then L equals 1 to infinity, BL lambda to the L, and N over V, which is the number density, that is equal to 1 over the thermal de Broglie wavelength cubed, L equals 1 to infinity, L BL lambda to the L. So, and remember that these B's, these are complicated integrals of the Mayer F functions, and those can be computed. So if you know the potential, then that gives you the F, and so you, in principle, you can do these things. Okay, so then you might say, well, I know how to proceed, because in fact we say, well, we've done this before, so this looks like what we did for ideal bosons and fermions. And so So that says we have the pressure is the pressure in terms of the fugacity, and the and we have an equation for the density in terms of the fugacity. And so that then says, then if I want to get P as a function of n, all I have to do is say P of n is equal to P of lambda of n. In other words, I invert the function below. I invert this. And you say, well, that should work, and of course the lambda, so this should work because lambda is then now just a function of n, and so everything works. So the question is that correct? And you might think, well, it looks very convincing. But it's not quite correct. Most people think it's fine, but it's not quite correct. So remember that these bees, let's go back a couple of slides. Yes, here we are. So here we are. Here's the bees. Look on the left-hand side. Look over here. Look over here on the left-hand side. And what you can see is that the bees are not just functions of temperature, but they're also functions of the volume. So then we get a complication, because if the B is a function of the volume, BL is a function of volume as well as temperature, then then we run into a problem, because what we want is to say that lambda is equal to lambda of n, and then eliminate it, but it's not true, because actually lambda is a function of n, but also of v. It's a function of v because lambda because the lambda is literally lambda of the cluster integrals, and the cluster integrals depend on volume as well as temperature. And so then I get P as a function of n, but also v. So if I eliminate lambda between those two equations, I don't get lambda as a function of n. Lambda is a function of n, but it's also a function of v. And that's kind of screws up the thing that we're trying to do, which is make an expansion. So, yes, quick question.
Not sure if I see why lambda is a function of b from.
Well, because n depends on the b sub l. Look on the left-hand side, b sub l and lambda of l. Okay, so if I invert that to get lambda as a function of n, I can do that, but lambda will also depend on the b's, and the b's depend on v. Okay, and they depend on v in a way different from just the dependence on n. Okay, but it's no big problem. Okay, it's not a problem. So you say, fine, no big deal, but it's not really a problem. Why? Because we defined the cluster integrals in such a way that BL of V and T, as I take the limit, V goes to infinity, that then is equal to a new function, BL of T, and I defined them with all sorts of weird factors so that would happen. Okay, so here, look on the left-hand side. There is my definition of BL. I sum all the L clusters, all these diagrams, and I normalized it in such a way. And the implication of that, if you go and look at what those integrals are, and you compute what those integrals are, and then you look at the factors of V and so on, you will see that the way that it has been done is in such a way that when I take the volume goes to infinity limit, that limit exists. So this limit exists. Okay? So by definition, by construction, this exists. And so we are very, very happy because now we can go ahead and do the elimination. So therefore, we take that limit, take this thermodynamic limit, so V is going to infinity, N is going to infinity, but the ratio N over V is equal to N is fixed. Okay, so that's what we're going to do. So now I'm going to say, okay, great. So then what I have then is that P over KBT is equal to 1 over thermal de Broglie wavelength cubed, the sum over L, BL slash lambda to the L, and N, which is 1 over V, is 1 over lambda cubed, then the sum over L, BL slash times L times lambda to the L. So that's great. Now, what we're trying to get, remember what is our goal? Our goal is the virial expansion. So we want to get PV over KBT is equal to 1 plus B2N plus B3N squared plus ... And when I write down little v is defined to be V over N, the volume per particle, which is 1 over N. So that's the thing that we're trying to get. And so you can say, wow, we can basically get that right away. Why? How do we get it right away? Well, all I need to do is just divide those two equations, the two equations in yellow. If I divide them, then so the strategy is going to be we're going to divide the P over KBT equation by the constraint equation. And that will automatically give us, on the left-hand side, PV over KT. So let's look at how that actually works. Now, so let me now make some comments. So in the virial in this virial expansion, the thermal de Broglie wavelength is absent. And in fact, what we've done is we've absorbed it. Into the bees. Okay, so let me just go that. Let me just do that. So the point is that the cluster integrals, these bees, do depend on the thermal de Broglie wavelength, and you can figure out from the definition by how much. In the same way that we've done before, where you take an integral and you rescale it, and you see how many powers come in front. So they do depend on lambda t, and from that you can see that if I define the coefficient AL of t times lambda t cubed to the power L minus 1, I define that thing to equal B sub L. then this quantity we will end up with a result that doesn't depend on the thermal de Broglie wavelength. So let me write that down. So if I do that, then I get the following. I'm going to write PV over KBT is then going to be the sum over L equals 1 to infinity A sub L, and then lambda T cubed over the volume per particle raised to the power L minus 1, and this is the same thing as the virial expansion. Okay, so I've just taken this equation over here, and then I've just rewritten it in terms of a dimensionless parameter. So the point about this, the reason I did this is that this quantity here, this thing is now dimensionless. And so just like we were doing when we looked at the quantum corrections to the ideal gas behavior, the lowest order quantum corrections. So we have an expansion parameter. That expansion parameter was exactly this. It was the thermal de Broglie wavelength cube divided by the volume per particle, basically saying that the particles are so far apart that they don't see the sort of cloud of quantum uncertainty around them, which is the typical size of the wave function that represents the particle in quantum mechanics. And so we can think of the particles as being classical. So that's just our definition. So now I'm going to, having done that, I'm now going to divide the two equations in the left-hand side. So PV over KBT is also equal to the sum from L is 1 to infinity of BL slash lambda to the L divided by the sum over L BL slash lambda to the L. So those two things, that's the same thing. And then, but what I've got then is that this thing is equal then to the sum from L equals 1 to infinity of AL, and then the lambda cubed over the volume, that I can get from over here. So that then is, let me put this in different colors so you can see it as I run over the edge of the page. It's that, so it's the term 1 over V to the L minus 1. That's basically what I have over here on the left-hand side. So what I have inside here then is L BL slash lambda to the L. Okay, all of these sums over L are dummy variables. So I could call the first sum over L, I could just rename L elephant. I could rename the second L in the denominator as hippopotamus, and the third L on the right-hand side as being kangaroo. They're all dummy variables. They're just summed over. So when I've written it down like this, I want to make sure you recognize that. And this formula that I've written down here isn't quite correct. What have I missed out? What I've missed out is that this thing, this term here is raised to the power L minus 1. Okay, so all I've done is I've taken this formula, there's one over here, and stuffed it into here on the right-hand side. And then I've used the dividing of those two things to get that. So basically what I've got is the ratio of two infinite sums equals the sum over these coefficients of another infinite sum that is raised to the L minus 1 power. And by the way, this is wrong here. I made two mistakes. One of them was intentional, one was not. I'm going to just erase this and I'm going to write it down properly. It's important that you see this. So this whole thing is then the sum from L equals 1 to infinity, A sub L, so that's this part, and then I'm going to put something in here raised to the power L minus 1, and the thing that I'm putting inside there is this on the from over here. So then I have the sum of m equals 1 to infinity m bm slash lambda to the m. That's what I wanted to do. Okay, and so in this case, I actually made the dummy variable different so that you don't get confused. Okay, so it's a horrible mess, right? It's the ratio of two infinite series equals the sum of coefficients of another infinite series raised to a power. Okay, awful, right? Okay, so what is the strategy? So what do you do when you have to? How do you solve this? So what you do is you take so if you call this as numerator over the denominator, what you do is you write that the numerator is equal to the denominator times the sum over L, AL, sum over M, M, BM, lambda to the M, L minus 1. So you write it like that, and then you equate powers of lambda on both sides, because these equations are supposed to be true for all values of lambda. So therefore, writing out the power series expansion, every term on the left-hand side must equal the terms on the right-hand side. So I just have to compute those coefficients. So I now have to work out what all those coefficients are. And so I will write it out for you, and then I will just tell you the answer. Okay. So what you get then, if you do that, is A1 plus A2 times the sum of m b slash n lambda to the m plus A3 times the sum squared dot times the sum over L BL slash lambda to the L, and that is then equal to the sum over, let's say, k equals 1 to infinity, b slash k lambda to the k. Okay, so that's what it is. And I have to compute, I have to equate terms of equal powers of lambda. And if you do that, here's what you get. A1 is equal to B1, and that turns out to be 1. A2 is equal to minus B2. A3 is equal to 4B2 slash squared minus 2B3 slash, and if you work out that is minus 1 over 3 thermal de Broglie wavelength to the 6th power, and then the integral of f something f11, f12, f13 times d3 r12, d3 r13, something like that. Doesn't really matter for now. A4 is equal to minus 20 b2 hat squared plus 18 b2 b3 minus 3 b4, and so on and so forth. And I promise you that you will not be asked this question on the final exam, how to derive, say, the coefficient in front of the B2, B3 term in A4. Promise you that. Okay. If you look at this coefficient A3, here's the miracle. You're not going to, since you haven't been exposed to the full horrors of this, you won't say why it's so amazing. But A3 turns out to be this diagram. Okay, and and why is it amazing? It's not a sum of a whole bunch of diagrams. And this happens. This is not an accident. So in fact, if you go to it's also in different diagrams, all the other ones cancelled. And there's no way you would know that. And so in fact, all the bottom line is that all these A4s and so on and so forth, these are all related to so-called irreducible cluster diagrams. And what those are is that I have the following. If I look at the second order, if I look at this order, so here is a diagram, and here is another diagram of 3 vertices. Okay, so this one is called irreducible, and this one is called reducible. And what happens is and what's special about the irreducible ones is that there's at least greater than or equal to 2 independent paths connecting all the vertices. And so this is another thing that you get from graph theory. And so the end result of doing all of this is that if we define a quantity which I'm going to call beta sub L, so this is the limit as V goes to infinity of 1 over L minus 1 factorial lambda t to the power 3 L minus 1 times 1 over V times the sum of all irreducible L clusters then if we do that, then the coefficients AL in the virial expansion are just this, L minus 1 over L times beta L. And that's the final result. So you can beat this whole thing down using tons of cool math. And so now you've got that. So now we say, well, okay, fine, so what? So here's the answer. Well, so now all we have to do is a few integrals. So let's suppose I say, well, I want the equation of state up to let's say 6th order. So basically, what I have to do is do just a bunch of integrals. To get these beta L's, and then I get a number, and then I'm done. And you can do them analytically up to, I don't know, I think when I think when I wrote these notes, B5 was known analytically, I think. And when I say that, I mean using the Leonard-Jones 612 potential. So what you want to do though, what you do usually is you compute these things numerically. And they're not that easy because they're in multiple dimensions and got multiple variables, and so it's a big mess. Okay, so Okay, so then you say, okay, that's fine. So, okay, so what? But does it work? Okay, so let's have a look. Does it work? So let's draw over here. How would we know if it worked? So I'm going to draw over here PV over N KBT. And I'm going to plot that against N, but N is not dimensionless. That's the number of particles per unit volume. So I'm going to multiply it by D cubed, where D is the diameter of the particles. It's either diameter or the radius. I've actually forgotten. I don't remember, and it doesn't really matter. Okay, so 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 that's the dimensionless variables, and this will start over here on the vertical axis. It will start at 1, and then it'll go up to, say, something like 12. And at low densities, you will have the ideal gas equation of state. So this will be 1. That's what we expect it to be. And if I compute just up to the second order, then what I get is something that looks like that. So that's computing just up to the second virial coefficient. So let's suppose you say, okay, well, fine. I've been eating my spinach, and I can really do fourth order. So you do that, and what you find is you go up to here, and then maybe you got a slightly higher result. So that's B4, and then maybe you say, well, okay, I can beat that. Aha. So you go a bit further, and maybe you get something like that. So that would be, let's say, B6. So that's the result. And then you turn to your friend who was born in the 20th century, or even maybe certainly the later half of the 20th century and perhaps the 21st century, and you say, work these things out. And they say, oh, that's easy. I just have to ask Claude Code to do it for me. And so Claude does it, does the Monte Carlo simulation, writes the code, and produces for you these data points. So so let's see what the real answer is. So the real answer is this, 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 something like that. Okay, so that's what you get from doing, say, a Monte Carlo simulation. So it kind of works, but it breaks down at high densities. Okay. Okay. All right. So basically, the bottom line, it works for small n. Oh, I know. I remember what d is. D is the average distance between the particles. I'm wrong about this. I don't know what it is. I don't remember. I'm just going to say radius. I'm confused. I will correct it in the lecture notes on Teams afterwards. Okay. Bottom line, this works for small n in any case, and so that's fine, but not super interesting. Now, what would be super interesting? Well, the answer is, what would be super interesting is if you could predict the phase diagram. So let's see if we can do anything like that. So here is the phase diagram of particulate matter. Okay, so let me just write that down for you. You've all seen this before, and you've all forgotten it. But let's just draw this curve, this thing like this. So okay, so here's the phase diagram. So let's label these different phases. So the phase diagram tells me what phase of matter I have when I've got the system at a particular temperature and a particular pressure. So what's going to happen is if I take a system at any given temperature and then I really squish it to high pressure, what's it going to be? What's that, Andrew? Solid, yeah. So this phase here must be solid. If it's a really low density, really low pressure, okay, then it's going to be something like a gas, right? And in this phase here, if I take the gas and then I increase the pressure, it will eventually become a liquid. So that's the phase diagram of matter. This this um, this phase boundary here is a first order phase transition. This phase boundary here is a first order phase transition. This boundary here is a first order phase transition. And this thing over here is called the critical point. And this point over here is called the triple point. Where three phases of matter all come into coexistence. So what happens beyond the critical point, if I go to temperatures higher than this Tc and this Pc, then I can go from liquid to gas without having any phase transition. So these lines here, what's important about them, and we'll talk about them next week, these things are phase boundaries. And that's where non-analytic behavior occurs. Non-analytic behavior of the statistical mechanics. And by that I mean the partition function, the grand partition function, and then all the thermodynamic variables that I can get from those things by differentiation. So that's the phase diagram of matter. Now, usually we don't think of the phase diagram in quite those terms. What we usually think about is what happens if I have the pressure as a function of volume. So let's have a look at what that would look like. So when we talk about the ideal gas, we talk about PV is equal to N kBT, and that means that the pressure is equal to N kBT over the volume. And this idea that the pressure of a gas is inversely proportional to the volume is what was known as Boyle's law. So basically it says if you have a gas and it's at a fixed temperature, if I change the volume by a factor of a half, the pressure will then double. That's what it says. And that's called Boyle's law. So that says, okay, let's have a look at Boyle's law. So let's now draw the pressure volume isotherms. So what we're going to do now is answer the question, what happens at fixed T? So we're going to now keep T equal fixed, and then look at what is P as a function of V. So we know what's going to happen for the ideal gas. So for the ideal gas is what we're going to get at very high temperatures. Okay, very high temperatures. You might say, well, my system is just, there's no interactions, everything is just ideal. So you might say what I'm going to get is just the ideal gas behavior, which is like that. That's my P is NKT divided by V. So that's the isotherm. That's the sort of ideal gas isotherm. And then you might say, well, why don't we lower the temperature a bit further? So let's now lower the temperature. Let's use a different color. Let's lower the temperature. And if we're going to lower the temperature, well, now the interactions are going to start happening. So we would expect that this curve is now going to deviate from this. So now we're at lower temperatures. And we're going to see deviations from the ideal gas behavior. So that's fine. That may be described by the van der Waals equation that we talked about last time. And if we go a little bit lower in temperature, what we're going to see is something that looks like this. We're going to see a kind of little kink here, kind of exaggerated like that. And then if I go to lower temperatures still, what we're going to see is this. Then flat, and then like that. And if I go to even lower temperatures, it's going to be something like that. Okay. What's say something else, question?
Sorry, is this why?
You mean, have I explained to you why it looks like that? I'm about to do that.
Oh,
Okay. And if I were to say, well, that's pretty weird. Let's join up these points where you get this flat behavior, then I get something that looks like that. And now we need to know some names. So this point here, where this point of inflection occurs, that is the critical point, and this is the critical volume, and this isotherm is T equals Tc. So therefore, this isotherm is T greater than Tc, and this one is T much greater than Tc, and therefore this isotherm down here is this one over here is T is less than Tc, and this isotherm here is T is much less than Tc. Okay, so that's what these represent. And so then you may say, well, okay, so I know what's going on. What is the reason for this flat bit in these isotherms? Anybody want to make a guess? So look at the picture above and think where we are. So we're going down in temperature. So I'm choosing a fixed temperature, and then so that temperature is fixed, and then I'm changing the pressure, and I'm changing the volume. I can change the pressure by changing the pressure, or I can change the pressure by changing the volume of the system. So I can do that. So all of these graphs are taken, choose a fixed temperature, and then look down here. So what do you think is happening, Josh? You have a hand? A phase transition between. So what's happening in the flat regions? Jake, yeah.
Sublimation.
Sublimation. Well, sublimation is when a solid turns into a gas. That can happen, but these one that's not on this diagram. In fact, we're not at low enough volumes or high enough pressures for sublimation to be drawn. It could be drawn on here, but I haven't drawn it. So, okay, if I take a liquid, I've got a liquid in here, believe me, okay, this liquid is in equilibrium, but it's not just liquid, right? What else is it?
Gas.
Gas. It's liquid and gas coexisting, right? So what's happening is at these points here, I'm going to draw a picture of this in a minute. What's happening is as I compress the liquid at constant temperature, sorry, forget that. As I compress the gas at constant temperature, what is happening is, first of all, the gas pushes back and the pressure increases. Then as I push down even more, then what happens is it goes through this phase diagram here. So imagine that we're at this temperature here below TC, and now I'm increasing the pressure. So I'm going in this direction, increasing the pressure. I'm doing it from here. So I'm increasing the pressure. Okay. So what's going to happen is I keep going up this curve. And then I get to this point. That point there, that green line, is a phase boundary. Phase boundary means the two phases coexist. So the liquid phase coexists with the gas phase. So now, as I change the pressure, or rather, now as I change the volume, I'm compressing the volume, but I'm doing this at constant temperature. The pressure doesn't change. I make the volume different. All that happens is I get more liquid rather than gas. I'll draw a picture of that in a minute. And then eventually I get to the point where everything, all the gas has been turned into liquid. And then now I've got just a liquid, and now I try to compress that, and then the pressure then starts to go up again. So what happens is I go up this dashed line that I've drawn here, then I sit at this phase boundary forever as I reduce the volume. So here, I don't want to make this totally messy, but what's happening here is the volume is being reduced. At constant temperature, but the pressure doesn't change. And the reason for that is two-phase coexistence. And that's what a phase boundary is. And then I come out the other side. So this part of the phase diagram is two-phase coexistence. And that's what's happening inside this thing here. And this purple line is called the coexistence curve. Okay. All right, let's see. Can I get any more things on page 202? I don't think so. Let's go to page 203. So you might then ask yourself, well, where is the critical point? Because that critical point tells you when you start getting liquid gas coexistence, when you get phase transitions. And as you can see from the coexistence curve, if I look at TC, if I look at the dP by dV at TC, that is equal to 0, and so is d2p by dV squared at TC equals 0. So that is the critical point. That's where you've got that very funny kink in the pressure volume isotherms. So then you can say, well, right, well, can we compute this? So now the question is, can the cluster expansion predict TC? And the answer is kind of. So let me show you the answer. So I'm going to draw a little table. So here is the highest virial coefficient that I go to. And then here I'm going to write down the value of KBTC, but it's got to, that's not dimensionless. So the only energy in the problem is the binding energy of the Lennard-Jones 612 potential, which we've called epsilon. So KTC over epsilon is a pure number. And if I compute to the third virial coefficient, I get a prediction for this is 1.445. I get a prediction for B4 is 1.3. For B5, I get the prediction 1.291. And then now you want to compare it with experiment. And so you say, well, wait, where does this model even apply? I never told you that. Well, it applies for certain types of non-ionic gases. So for example, the noble gases it would work with. So you could look at, say, argon, for example. So the gas argon, that is well described by the Leonard-Jones 612 potential, and for that we know the value epsilon, we know the value R naught, and so we can compute that KBTC over epsilon should be 1.26. So it's not quantitatively very accurate, but it roughly gives you the trend. It's not super amazing. And so you have a lot of work to do to be able to even predict to predict this. So it's not super amazing. We're at about 2% accuracy up to B5 or B6, something like that. Okay, but then you could say, well, does the cluster expansion predict what happens below those temperatures? And the answer is no. Okay, so that's fine, but there's a bigger problem. It doesn't predict the phase transition behavior at all. And I don't want to, for now, go into why it doesn't do that. I will come back to that later when we talk about phase transitions a bit more. But for now, I want you to hold this in your head. We did all this work. We did all these nice diagrams and graph theory and fancy integrals and stuff like that. So in principle, we know what we're doing. It works okay, but it doesn't really answer the most exciting question. And so, if you want to do it, fine, but it's not super exciting. Okay, so now let's talk about something that is much more interesting, and that is charged fluids. The thing I want you to remember about this lecture and last lecture is diagrammatic perturbation theory is most interesting when it breaks down. Then it's telling you something interesting. And the reason why it's telling you something interesting is this. Diagrammatic perturbation theory makes assumptions about analyticity. And when a theory which is based on analyticity breaks down, it must break down because there is something non-analytic happening. And if something non-analytic is happening, that's what we mean by a phase transition. So the breakdown of perturbation theory is the interesting thing about it, not the specific thing itself. That's my personal view. And in fact, all of the interesting phase transitions that are discovered in matter are discovered by other methods. So let me give you an example in condensed matter physics. So some of you will be or are maybe condensed matter physicists. Okay, condensed matter physics. Why we go into condensed matter physics is about, roughly speaking, every 5 years, we discover a new state of matter, a new phase of matter that we didn't know exists. By now, of course, they're getting really, really exotic and amazing and interesting, but that is still going on. And the ones that we teach in courses like the ones I teach on emergence and so on, in those courses we teach about the superfluid transition, the superconducting transition, maybe the quantum Hall effect, things like that. All of those things, the people who solve those problems ended up getting the Nobel Prize for working out the theory of them, and they never use any of these techniques. What they used instead were non-perturbative methods, such as variational methods. All right, now let's talk about charged fluids. So this is really super interesting. We're going to see a way in which all this math can break down in a very simple system, one that's so simple, in fact, that you have it all over your body. You are basically all of this. So what we're going to talk about now is the application of this many body theory to particles with long range interactions. And why are we doing that? Well, what we did up to now, we were talking about short range. We're really looking at L. Leonard-Jones 612. So we had a hardcore repulsion, which we model as a 1/r to the 12th power law, and then a long-range attraction, which was r to the 6th, but it's still very quickly converges. So if we now say, well, what about Coulomb forces? So Coulomb interactions, those go like 1/r, not 1/r to the 6. So they extend much further. And you might think that it might break down. So why would you think that? Well, you might think that because remember that this expansion that I showed you, I told you it's called the cluster diagrams and cluster integrals and cluster expansion. And basically what we're saying is, I've got, let me just go write down the answer. Clusters may not exist in any real sense. So let's think about why that's the case. So here's our picture of the system. And you'll remember that I did this. Remember, I did a 10 seconds theory for you of what is the 2-point correlation function in a dilute gas. And we found that it was e to the minus beta times u. Okay, so what we did there was we said, here's all the particles. And then the most dominant terms in the integral are when I've got two particles that are close together. And then I can compute the interactions of those. And I don't need to worry about all the other interactions in the system because all the other particles are far apart. So that's true. And so you can think of this thing over here. This thing over here is kind of like a little cluster. And then when I go to these higher order terms and higher densities, you might say, well, now I'm looking at the contributions from terms like this and this and this. And that might be what I mean by my cluster. And so I'm looking at the contributions to the statistical mechanics from these clusters of particles. Okay, so the idea is that I can separate the system up into particles that are strongly interacting because they just happen to be close by to each other, and then particles that are weakly interacting because they're far apart and they're dilute and they hardly ever see each other. And as I go to higher and higher densities, what I need to do, as I go to higher and higher densities, what I need to do is to include clusters of more and more particles, B2, B3, B4, B5, B6, and so on, okay? So you might say, well, if I've got a long range interaction, then maybe everything is just one big cluster. So that's the intuition. That's why we asked the question. So let's go and calculate that. So what we're going to do is we're going to compute B2. So B2 was the second virial coefficient. That was the one that I derived for you last time, heuristically, without doing the full Mayer cluster expansion. And remember, we derived this as the following: e to the minus beta u of r minus 1. So that was the second virial coefficient. Okay, so that's the thing that we derived heuristically, and then we saw that emerged quite naturally from the systematic many body theory. So let's suppose now that we say, well, okay, long range interaction, long range Coulomb interaction. between charged particles in, say, an electrolyte or something like that. So I'm going to just say that beta u of r is some number divided by the absolute value of r. So then now I compute what is the Mayer f function. So Mayer's f function, if you remember, looks like this. So I drew it for you last time for the Leonard-Jones 612 potential, so it looks something like that. And if I were to draw it for the Coulomb interaction, well, it looks something like that. And we can actually see that explicitly. So let's write down what the Mayer f function is. So I write down minus 2 b2 of t. So that is the integral from 0 to infinity e to the minus a over r minus 1. And then I've got 4 pi r squared dr. So that's doing the integral to compute the second virial coefficient. And then I'm going to write this in the following way. So this I can write as the integral from 0 to some number a. Doesn't matter what a is, as you'll see. And then e to the minus a over r minus 1 times 4 pi r squared dr plus the integral from a to infinity of e to the minus a over r minus 1 times 4 pi r squared dr. So that's the second virial coefficient. And what is a? Well, a can be anything you like. So I'm going to say we'll choose a as say some number between 0 is less, a, like this. So choose a to be a number such that that when a is less than r is less than infinity, the exponential in the second integral can be easily approximated. So there's no scale in this problem, so I can choose a to be anything I like. So this is an exact statement. The point I'm making, though, is that this term over here is finite. So it's just some number. We don't care about that, but I do care about this term. So let's have a look at the second term. So the second term is this. So minus 2 b2 of t is equal to whatever this first term is. I'm going to call it f of a. And then I'm going to expand the exponential in the second term. So I've got the integral, and then the integral is 1 minus a over r plus 1/2 a squared over r squared minus the next term, and then minus 1, and then times 4 pi r squared dr. So that's my integral, and so now let's have a look at the second term here. So you can see that the 1 cancels from here, and so this thing is then the integral from a to infinity of minus a over r plus a squared over 2 r squared times 4 pi r squared dr. And this integral is divergent. Because you can look at the first term, and that's the first term is going to go to a over r times r squared, that's a times r, integrated from dr from a to infinity, I'm going to get infinity. Same thing with the second term, it's also going to be divergent. And so it looks like this is divergent. Question.
Yeah, you did just approximate from the.
What?
You did just approximate from the main.
Yes. The remaining terms are higher orders in 1 over r cubed.
Okay, so it's not.
So they're not going to diverge. Well, the r cubed one, the r cubed one will also have a logarithmic divergence, but the other ones will converge. Okay, so there's terms here plus order 1 over r cubed. So it's not it looks divergent. It's not it's divergent, but you have to be more careful. Well, I just want to explain to you why you have to be more careful. This isn't a place where I want to go into a lot of detail about expansions and asymptotic series and summability and so on. But let's suppose I gave you this series. Suppose I gave you this series, 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. So I gave you that, and I say take x goes to infinity. Okay. So then you might say, let's call this quantity I. Okay. So then you may say, aha, I is infinity, because, well, if I take x goes to infinity, the first term is infinity. Second term is infinity. Well, it's actually infinity squared, and so on and so forth. So obviously, this thing makes no sense. But in fact, the answer is that I is equal to 0. Why? Somebody who's looking bored, tell me why I is equal to 0.
It's alternating series, and then that's like the series from cosine.
It's not the series from cosine.
The minus x, right?
Say it again?
The minus x.
Yes, it's actually, we can sum it. So I is actually, we sum. So there's something happens. And then it's actually e to the minus x. So e to the minus infinity is equal to 0. So I can take an expansion and I can say this, I can resum this expansion and find out that this is actually a representation of something. And then I can work out what that is and then see what its value is. So just because the terms diverge does not mean that the sum of the terms is equal to infinity. Okay. But in this case, so I'm not going to, you can do various tricks to sum these terms and then renormalize them and so on. And this is what is done in many body theory and stat mech and field theory, and we're just not going to go into that. Okay, so basically the result is essentially correct. So I'll just say directionally correct. Well, there is a problem. And so next time, what we will do is we will solve this problem. Of a charged fluid. So let me tell you how you really do it. So the real way you would do this is you take this series, you look at all these diagrams, you sum them up, you do a normalization theory, you resum the thing, and then you find a finite result. Okay. in the quantum version of this problem, that was done by Murray Gell-Mann and Ken Buchner. Actually, they, at one point, Buchner was here at UCSD, so maybe, but I think this was earlier than UCSD existed. Yeah, it was earlier. So they did that calculation, and so you can do it. There's a much more physical way to understand what is really going on, and that's what we'll talk about next time. And we're going to solve this using high school algebra. So, but the important thing that we're going to learn about is we're going to learn about screening and a charge renormalization. But there is a problem, and you can sum. So the amazing thing is, I just showed you the divergence of the second diagram. The second cluster integral. You can sum all of them to arbitrary order and then solve this problem. But it's a huge amount of work to do that, and very, very subtle. And so we're not going to talk about how you do that. Okay, so that's it for today. So let me just turn off the recording.